Hi everyone, this is my 145 project on converting an inference script from Python to Rust. So first, a little bit about me. My name is Sia. I'm a third-year undergraduate computer science major, and I've been a sub-project lead in acoustic species identification, which is one of the projects in the Engineers for Exploration Lab since winter of 2025. Some context for acoustic species is that there is widespread biodiversity loss, and our collaborators at the San Diego Zoo Wildlife Alliance want to find a way to use audio to monitor species like birds in a non-invasive, non-labor intensive ways. They do this by deploying audio acoustic loggers in natural habitats and accumulating terabytes and terabytes worth of data. But what do you do if it takes a manual labeler 3 seconds to label 1 second of audio data? That means it would take them 187 days to label all the data, which is simply not feasible. The mission statement of Acoustic Species is to use ML to automatically label these bird calls. When I joined the project team, the inference script had already been trained and tested in Python, and my efforts went towards building a desktop app, which allowed collaborators to run inference on their own machines. The problem is that collaborators want everything to remain on device, but the current inference pipeline runs on a remote server. This led to my entire project statement. Can I convert the inference script from Python to Rust to make it faster, self-contained, and easier to deploy? Rust was chosen because it's fast, memory safe, and has good developer tools for running inference. This is a demo of the desktop app where the model has not been integrated yet, but we would like that our collaborators could upload audio data, run the model on it, and then save the final classification in a database. Um, some high-level overview of the model is given an audio file. We transform it into a MEL spectrogram, which is basically a visualization of that audio that is more attuned to how humans actually hear. We then use that MEL spectrogram as an input to EfficientNet, a popular computer vision model to detect which bird species are present in each audio file. For the pre-processing, Python accomplishes this using lazy transformations, which basically defers the creation of the spectrogram until it is needed, aka in the inference script. Rust does not have this capability. In fact, the pipeline that I did was using a PY03 wrapper to import the spectrogram logic, convert the MEL spectrogram information, and save it in NPY files and use that as the input to the ONNX runtime model. This does lead to some memory head since the spectrogram information is saved in files. However, memory is not the bottleneck for this project. In fact, speed and deployability are the priorities which are not present in the Python version. Additionally, if memory ever does become a bottleneck, you could bypass that through caching or quantizing the model. The next step was importing the Python inference code using ONNX runtime and running inference. ONNX runtime is basically a platform that allows you to share inference code amongst different platforms without the training code. And finally was the post-processing, which identified the species with the highest predicted probability and stored that as the final classification result. So you'll notice over here that Rust consistently outperforms Python after about 1.5 epochs, and that is true even without any sort of GPU acceleration. And there are three key reasons why Rust achieves this speedup. One, there is no interpreter overhead, which is native to the Python language. Two, the spectrograms are pre-computed. So they are a one-time cost in Rust, causing the singular epoch to run a lot slower than the Python epoch, but they're a consistent cost throughout Python, which is why as the number of epochs increases, the Python implementation takes much longer. And finally, the Rust implementation runs the model through ONNX runtime, which is optimized for inference under the hood. The next thing I want to know is there is a linear trend in both these curves, and that tells us two things. One, there is no caching in either implementation. Each epoch runs independently and takes roughly the same amount of time. Secondly, because of that, we can assume that Rust will continue to scale better over more epochs and larger data sets, which is exactly what we had wanted to accomplish. Now that the Rust inference script is running and it's running better than Python, the next goal is to actually integrate it into the desktop app. Once that is complete, I would like to further parallelize the Rust script. As you can see, both the Python and Rust script severely underutilize the CPU, hovering around 5 to 10% utilization. Regarding the GPU, the Python does use it for a brief amount of time and then doesn't anymore, whereas with Rust, I didn't get time to implement any sort of GPU optimizations. So utilizing the CPU, GPU, and multi-threading would be a good next step. Once all of that is completed and tested, I would ultimately like to give this desktop app to collaborators outside of San Diego to not only receive more feedback, but to see if it truly can be a viable option for monitoring global biodiversity. Thank you.